So I got a few emails from a gentleman from Boston, Massachusetts, John. I told him I would go ahead and reply to his emails with a little talk here. I think it's good practice to get the ideas out in the open so everybody can see them instead of private conversations. Of course, with limited, I should say like understanding who the people are, because I know a lot of people don't like to be thrust out in the open. So I'm kind of cool with it. I don't really mind anymore. People are gonna say what they want anyways. Hi Celeste. Now, John had a few questions here and a few corrections for me, and I want to just lay out my reasoning for some of it. And it's not like I have the answers, because I don't. I have a few of the missing puzzle pieces to a much larger puzzle that hasn't yet been fully assembled, or we don't even have the big picture yet. But I like to believe that I have a few pieces to the puzzle, and they could help people out significantly if they just should quiet their mind a little bit and realize that the authorities, they can be lost sometimes, and it's okay to call them out. But to say the authorities are never wrong and that they have all the puzzle pieces is untrue. The authorities don't always have the big picture in mind. They don't always have all the pieces of the puzzle. So it's in our best interest to sort of set our ego on the shelf and listen sometimes. And I think that's good practice with literally everything you do in life. If there's an idea out there, you should just set your ego on a shelf and just listen what the person has to say. If you don't, well, you might miss out on something very important. Continuing on, he asks, do white dwarfs inherit the same stuff? He says he understands the idea of different transformation curves, and he also asks, do all stars start out the same, or is each star's guts unique at birth? Do white dwarfs inherit the same stuff? Not sure. My original idea for white dwarfs, the very beginning on this graph, was that some of them are so dense, so electromagnetically influential that they can do some really strange things that I just don't understand at all. A white dwarf is supposedly extremely dense and extremely hot. We're talking many times the density of gold, as well, 100,000 degrees Kelvin on the surface. So we're talking an object really, really exotic here, something that I have to admit is just beyond me. And I think the white dwarfs, I think, are probably beyond me. The best I can do with white dwarfs is to say that they're probably electron degenerate matter, meaning in an atom you have your nucleus, your nuclei, the nucleons, I should say, the protons and the neutrons. But with a white dwarf, the electrons are removed from the atom, so all those neutrons and protons are really close together. And I think what actually happens is that maybe some random material might enter into the white dwarf and cause a really big explosion event, because when you add a bunch of electrons all at once, it's going to be a pretty weird event to happen, and there's a cascade of other processes that are caused by objects interacting with white dwarfs on their surface. Some very exotic physics, I think, is going on there. Definitely over my head, but it's definitely something that I would stress for people to read up on and to look at. The only issue with white dwarfs I have, mainly in opposition to the dogma, is they believe that a white dwarf is the end of a star's evolution, which is completely 100% false. A white dwarf is extremely energetic, it's extremely dense. If anything, they belong in the beginning of a star's evolutionary history. Actual dead stars are made of rocks and minerals, and us. But actual dead stars have extreme ages, are really cold, rocky, and they're really small. Those are old stars. A white dwarf is not a dead star. I don't know why they allowed that to be taught in academics. Each star is unique, is each star's guts unique at birth? I don't know. Do all stars start out the same? For the most part. Hot, big, extremely energetic. But that's more of a vague kind of thing. Like, do they start the exact same size? Are they 1,000 meters wide? Are they 10,000 meters wide? Are they 100,000 meters wide? I'm not too sure. Stellar birth is very, very exotic still to me, even to this day. I leave it to somebody more intelligent than me to figure that out, or dare I say, more lucky than me, because it takes luck to pull some of this stuff off. I'll admit that. It says here, I think a gravitational event could rescue a star from a fast transformation curve and put it back into a slower transformation curve. Do you think this is possible? Yes. A fast transformation curve. Remember, it isn't that a transformation curve, it isn't that they stay on the same transformation curve. They can drop down to a lower one, or, what I mean to say is they can drop down to a lower transformation curve, and I know he addresses the fact that I say lower, but it can drop down, but then it will still evolve slowly after that. It's not going to continue going down straight down. So I don't want to draw on this one. Dang it. Let's see here. Do a rough sketch for you guys. Why didn't I just do this before? Okay. So what I think he's asking me is this. Here's the top of the WT diagram. Now, it isn't going to be like this with every star. It isn't going to be a smooth transition. It isn't going to be smooth. But what I think he's saying is it could start out as a slow transformation curve. A slow transformation curve, and have a gravitational event happen, and then move towards a little bit of a faster one. Of course, that little event right there would be the gravitational event, and that would be up here somewhere. Because if it happened down here, it wouldn't change too much of the star's mass. The gravitational events that would significantly change the star's mass happen early on in the star's metamorphosis. So to go over that question again, hang on, let me. Could a gravitational event rescue a star from a fast transformation curve and put it into a slower one? So basically, from fast to slow. So what he's saying is, here's a fast one. The fast would be down here. What he's asking me is, can it go from a fast one and then get bumped up over here? So basically, do one of these numbers. He's asking me, well, can it be destined to go down here, but then go slower? Yes, this can happen as well. It can move up to a slower transformation curve, but keep in mind the whole curve itself won't change. Like, it won't go up. In other words, remember, this is time. This isn't the addition of mass or subtraction of mass. This on the x-axis is this time. Hopefully I can answer that question better in the future. Put another way, is there a factor that can pull a star from a slow transformational path into a faster path? Well, yeah, a slow transformational path into a faster path is definitely possible. If Earth was on a faster path, it wouldn't be the size it is right now. It would probably be Mars' size. So given Mars and Earth have both the same size iron-nickel core, which signals that they were as once in their gas giant phases as big as each other, but Mars had been adopted by a hotter host and had its outer atmosphere ripped away a lot quicker than Earth did. Earth had the time to build up the rocky mantles, or the rocky mantle, and have a lot of material to work with. And he says, time location of your comments is 230 to 240, and why are moons and planets different sizes video? He says here, you have previously stated that stars are born as white dwarfs and that they expand into giants until they reach some kind of gravitational enthalpic equilibrium. But in the video, you present new stars as starting off their lives as giants. All these stars start off as really, really big, hot, and bright. It says here, if your hypothesis posits that all new stars start off as white dwarfs and expand to be giants until the point of equilibrium between gravitational and heat factors, then the Walensky-Taylor diagram should reflect this more accurately. As to say, the star highest on the y-axis should be noticeably smaller than the next highest star on the y-axis. Let me read that over again. That is to say, the star highest on the y-axis, that's the blue giant, should be noticeably smaller than the next highest star. Next highest star. Well, here's the thing. I don't know exactly if white dwarfs are the beginning of star evolution. I think there's a possibility they can be, but I know they're not dead stars. You can wipe that dead star crap and throw it in the trash, because we discovered what dead stars are. So when I had to put a white dwarf in a certain spot, and I found out that they're in orbit around other blue giants, I thought to myself, well, blue giants are really young, and white dwarfs aren't dead stars, which means those two stars were probably born at about the same time. And then it didn't make any sense to me, because I was like, okay, well, like Sirius A and Sirius B, go ahead and look those up. You'll see a Sirius A is a big blue giant, and Sirius B is a little white dwarf, and they're both in orbit around each other. But Sirius B, its mass, I think, is around half the mass of the sun. It can pull that blue giant in just as easily as something that had half the mass of the sun, even though the white dwarf is really, 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 really small in comparison, like the actual physical diameter, not its mass. And this is the really, 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 really crazy part that I'm not expecting my listeners to accept, or physicists or anybody that's taken basic physics or anything like that. But there's something very strange about white dwarfs. I think they probably ignore mass conservation. I think there's a property of extremely dense material that white dwarfs are composed of that makes it to where they can mimic mass, or they can remove the properties of mass. For instance, if a white dwarf, scientists say the white dwarf is half the mass of the sun, being that it's so dense, that material gives different properties to make it look like it's only half the mass of the sun. But in reality, a white dwarf is probably more massive than a blue giant. And what that means is that you can't look at its physical size as being relevant. It would be like comparing a little nugget of gold, like a gold nugget, to a really large helium balloon. The little gold nugget will have just as mass as that big helium balloon filled with helium, but the helium balloon is a lot bigger. And that's the really strange part. And I have mass loss as being on the x-axis, mass loss going down, and of course mass gain going up. But then again, I don't think it's that the white dwarf gains mass. I'm really seriously considering that the white dwarf, it's a type of exotic matter, and if we can figure out how white dwarfs actually, how the atomic material arranges itself in a way to where it can remove the mass that we supposedly say is missing, then we could possibly figure out how to make inertia cancellation devices, and we can mimic craft that can, accelerate at extreme velocities, as Commander David Fravor did. He was a pilot in the Navy, and he had chased one of those UFOs. But the UFO could travel, at extreme velocities, like that, and you can't do that if you actually pilot it in a regular craft that obeys, the laws of physics as we know them. But what I'm saying is white dwarfs are probably showing us new laws of physics, in which the concept of mass conservation is kind of ignored in a weird way because the material is very exotic. And I wanted to always keep that door open with white dwarfs. I didn't want to go too crazy with them, because that's the way my mind works. If I think about something too long, like something very exotic like that and very different, I just kind of lose track. I don't want to talk about it too much because it's something that really, really bothers me. But one thing's for sure, keep white dwarfs in front in the beginning, and I think you'll be doing good. They're not dead stars like the dogma is saying. Finally, higher-lower language is ambiguous when describing transformational curves. It mixes categories such as speed, height, and time, and almost requires a visual reference to the Wolinski-Taylor diagram in order to be correctly interpreted. Maybe better is faster, slower, much less ambiguous, and can be understood without visual reference. I agree, yeah. Slower and faster because the x-axis is time. So instead of me saying higher and lower, it could be slower and faster. Faster would obviously be the lower part, and slower would be the higher part. Think if you have more time, you can make a bigger object. If you have a lot less time, you rush around and you can't make anything really significant happen. All right, I think I rambled enough for that. I hope that helps John. If anybody has questions, feel free to ask them. It definitely helps me kind of sort out my mind a little bit, and it helps other people out if there's other ideas they may have. It might spur them to think about these issues in a different light as well. All right, you guys, take it easy.